Hello. Good afternoon, everybody. Thank you for coming for our presentation. I know it's challenging to attend the very last session of the conference, so I'm glad you came. I'm Henrietta Dombrovskaya. I am the Senior Data Architect for Braven Holding in Chicago. And my partners in crime are Chad Slaughter from Scale Genius, sitting right here, and Boris Novikov from University of St. Petersburg, North Florida, Russia, and the School of Business, Alta School of Business in Helsinki, and a couple of other places. We all got together to put up this presentation because that's something which we are really passionate about. So the topic is, as you can see, the enhancement to the bitemporal data model. And that's a long title for the presentation in lots of words, okay? And we're not sure what they mean. So let's talk about what this will be all about. Okay, what is, now it's not working, okay. Incorporating time in relational model is actually a hot topic. It might be that you never heard about this, but if you think about, do you want to have time dimension as an extra bonus in your data model, you would probably say yes. And most of people actually say yes, especially know-whom financial people. What they want to know, why they want to incorporate time in their model. Like most typical thing, did you guys ever face this? So this report looked different last week. So last week I ran exactly the same report with same parameters and it looked different. What happened? What changed? Can we run this report exactly as it looked a week ago? So very typical, that's like called the snapshot query. So running some query as if we ran it like a week ago, a month ago, last quarter, etc. The time interval queries, so basically we need to know what happened through the time. So we, for example, we had something, we had a query, now it runs way slower, and what exactly changed with data that it becomes slower, how the data changed through the certain interval of time. So those are time interval queries. Correlated time queries that are actually most interesting, most difficult to put together in a relational system. So what was happening, and now we do not set up the time as in snapshot queries, but we want to know what happened simultaneously with something else, okay? So like how many people got fired since X became the CTO of the company, how many people left voluntarily since Y became the head of analytics, etc. So very interesting queries. You know, you can get lots of interesting information like this. And most of big giants, most of big databases at least claim they do have support of time. They have it naturally built. Like DB2, Oracle, they at least say they do, and also after going back and forth, supporting time was included in the SQL ANSI standard, so starting from 2011. That was the last time. It had been there before, then it was removed, now it's back. However, surprisingly, Postgres never formally included time dimension. Again, we all saw lots of like experiments with like time series, time travel, and we saw this, but we never had time as an integral part, like time dimension as a separate feature of Postgres. And that's what we are going to fix, because it's a shame that they have and we don't. And actually, we can do it much better. So let's see how we can do it much better. This page represents the references for works which were done on the bitemporal data. So basically, we want to say we are in a very good company. There are lots of people who were working on incorporating time and incorporating bitemporal data, so two time dimensions at the same time. Oops, hold on. Wrong one. Okay. This work, as you can see in the title, is enhancement of bitemporal model. And last year, we presented a similar talk on the previous PG Open. And so now I will give like a quick overview. Actually, my task today is extremely challenging. It will be very loaded because I basically need to make like 3 presentations in one. Because unless I will fill you guys in on what was happening last year, like it doesn't make much sense to tell what are enhancements if you do not know what we are enhancing. And then we enhanced it in like 2 different ways. So this is like previous work overview. So what we can say, if we look at this literature, which I kind of briefly scanned on the previous slide, there are lots of surveys which address how different databases represent time. And surveys say actually Postgres has everything to like naturally incorporate time, but it does not. And that's right, actually. Postgres is very well suited to support time dimensions due to existence of GIS indexes. And when we started to implement this model, we utilized it like to full advantage. So we heavily rely on the features which are already present in Postgres. And we used our implementation. So we based it on the asserted versioning framework. Again, I will upload the slides, and you'll see the reference to this work. This is not actually NC standard. We think it's better. We think it like does the work better. That's why we chose this one to implement in Postgres. And that's where our work can be found. So we have a public Git repo. It's Scale Genius PG Bitemporal. And what we have there, we have the definition of our time domains, so how you can set domain for your application. We have implementation of NN algebra of intervals, because Postgres does have some of these functions, but does not have everything, and for some of them it's a little bit different from like classical add-in definitions. So we have this, and then we have implementation of the basic operations of the bitemporal data model. So create bitemporal table, insert, update, correction, inactivate, and delete, and also the newest edition, support of bitemporal constraints. That's like the most interesting thing, I think, that's new. So let's take a quick look at bitemporal operations. So first of all, as I said, we use asserted versioning framework, and we use specific time dimensions. So we use effective time and asserted time. And one of the problems with supporting time is that the definitions are very overloaded and non-specific, because you could hear application time, system time, like valid time, etc. And different people, different researchers, different practitioners mean different things. So we use the definition from this model. Effective time is basically when we believe these like events took place, or when we believe those were the values for certain objects. And asserted time is the time when we asserted this is true. So I will give you examples, and you will kind of get better feeling about what exactly we mean by asserted time. And the other definition we introduce, so effective time plus asserted time, we call it time regions, because if you can think about it, it's like 2 dimensions. So basically you can think about this as rectangles of time. So that is bitemporal insert. So today is May 1st, 2015 on this picture, and a bitemporal insert is actually not that much different from regular insert. There is one record, we want to insert a record about customer, and we insert this record. The only difference is that we insert also 2 times, asserted time and effective time. And right here you can see what is the difference, because we want this customer like to indicate that this customer start date is June 1st. However, today is May 1st, so we are inserting it as effective time from June 1st. But we know about this starting from today. So today is the start of assertion interval. At this time, this record is visible in the database. And the graphs below, they identify how they indicate how it looks when represented graphically. Bitemporal update, now it becomes more interesting because meta does not disappear in our model. So when we update, we do not override things. We keep track of how the data looked like before, because remember, financial people want to see how this report looked last week, last quarter, last November, whatever. So what we're doing here, so now we are saying that today is September 15th, and starting from today, this customer type is changed from silver to gold. We are not overwriting the value silver. Instead, we end assertion interval. So we end the assertion interval. So we're saying that that's what we thought. So before September 15th, we asserted that this customer is silver from June 1st to infinity, to forever. Now, since today, we assert that he was silver only from June 1st to September 15th. And now, from September 15th to infinity, we assert that the type is gold. Okay, all good. Now you can see how the time regions change. So we did have one time region. Now we have 3 time regions. So each of them are marked according to the table above. So the first one corresponds to first record, second to the second, and third to the first. So third is our infinity. Bitemporal correction. So now, remember, instead of insert, update, delete, we have 5 operations for bitemporal model. So why we need 5? What's the difference? Here is the difference. So, okay, so we lived happily for a week. Today is September 22nd. Oh, shoot, actually, we messed up. He is not gold. He is platinum. And he never was gold. It was a mistake. We just put this information there by mistake. So how are we going to fix it? We want to make sure that he is now platinum in our system. However, we want to keep track that for the week we had a wrong assertion about this, because at some point somebody ran some reports and some got him counted as gold, and now actually it's wrong, he's platinum. But we want to make sure we can go back and replicate our erroneous results. So what we're doing here, again, the first 2 records are the same because we're not touching his silver status. Now we're doing bitemporal correction. So we are saying this record was asserted like this for 1 week from September 15th to September 22nd. And at this time, we asserted that he is gold. But actually now, starting from September 22nd, we assert he is platinum and he never was gold. So important thing is that here you can see that the effective interval for these 2 records is the same, because that is the correct effective interval. But assertion was wrong. And look now down here. So now instead of 3 intervals, we have 4 time regions. So that's the 3rd time region changed. So it used to be like this from infinity to infinity and to infinity. Now that is our time region, and that is our new time region 4. Okay? So that's bitemporal correction, bitemporal inactivation. So now you can kind of figure out, because update and correction kind of goes hand to hand. So bitemporal inactivation and bitemporal deletion also go hand to hand. So again, meta doesn't disappear. So today is November 5th. Now we are saying, okay, this customer won't be our customer after the end of the year. So what we want to do now, we want to end date his effective period. So that was our previous record. We asserted like platinum forever. Now today is November 5th. So we end this assertive interval and we include new one. And now we're saying, so now we assert that he is effective only till December 31st. And after that, he is not our customer anymore. But because we assert this to infinity, we will still see this customer information. We'll just know that he is not active anymore. So we inactivate him. Now, okay, so now we have, how many intervals? 1, 2, 3, 4, 5, okay? So now that is the interval when he will be like not there, but we will still see him. And then we are saying, okay, actually, no. Now, next thing, bitemporal delete. we do not want to see this information in our reports any longer. So today is November 17th, and now what we are seeing here. So we are changing this last record. How we change it? Effective is the same, nothing changed. Is customer until December 31st, but we close assertion period. So now look here, we cut one more rectangle from our time region. So now there are 5 time regions, and each of them correspond to the record with the same number, and that's how it goes. Okay, so far so good, right? So that's how bitemporal operations work. Now, bitemporal constraints, and that's now we're coming to the interesting part. It's still overview of what we did last year, but now we are coming actually to the most interesting part. So we actually know how to create table. We know how to insert, update, delete, correct records. Now each respectful database should allow to support different constraints in how we support bitemporal constraints. So we need to support all normal constraints, right? Primary key, uniqueness, check, null, not null, and foreign key. Primary key and uniqueness is supported with exclude constraint with using gist index. Again, I would not go into details, but basically that's how we define the bitemporal table. It should have the business key, which would be primary key in non-temporal table, but we also add the exclusion constraint based on gist, so like the combination of asserted and effective ranges will never overlap. So time regions assigned to each record will never overlap for the same value of the business key. And for uniqueness, it's exactly the same, because guess what? As for normal relational database, for normal table, what is the primary key? It's one of the unique constraints which we assign to be the primary key. So same here. There is no difference between supporting the primary key and unique key. It's just basically it's just in the words. Okay, the null, not null, and check obviously have no difference, same ways as we do it for regular tables. And foreign keys is the most difficult and most interesting. I will tell in a minute why it's most difficult and most interesting. So other thing, we have some meta code to support, not to support actually constraints, because constraints should be in PG constraints table, and we are not part of Postgres core, not even the contrib model so far, so we cannot introduce our new constraint types. So what we are doing, we are mimicking our constraints by adding check constraints, which have the specific syntax which we specify in the functions, and they are always true, but when you issue describe for the table, you see these constraints, you can read it, and you can see what is the primary key, what is the unique, and what's the foreign key. So that's the purpose of this meta code for the constraints. Now, why defining foreign keys is difficult? What do you guys think? What's so difficult in defining foreign key? From the first glance, okay, same thing, right? We need to make sure that we have a matching value in the parent table. Not exactly, because also we need to make sure that the time region for the child record is included in the time region of the parent record. So it only can be valid as long as the parent record will be valid. And you might say, okay, what is the problem? Okay, you just can make sure that interval is included. It is a problem, you know why? Because it's not like one solid interval. Let's look at, okay, we are doing online lending, so we store data about loans and payments. So let's say loans and payments are bitemporalized. So my foreign constraint is loan ID on the payment is the foreign key for the loans table. And yes, there should be loan if I make payments. However, how many records with this loan ID we have? Multiple. And they will be all valid. It's like loan status will change, loan will be approved, active, declined, closed, whatever. So there will be multiple records and multiple time regions associated with this loan ID. And when we insert payments, we need to make sure we're inserting and this time region is enclosed in God knows what, actually. I'm not sure what geometrical form this set of time regions will be. And this actually turned out being a major problem where we've been, like, stuck for a while. We kind of proceeded with foreign key creation until this very last moment. So how we create foreign key constraint. Actually, if you know how the foreign keys are created, like inside Postgres, like normal foreign keys, that's basically the same thing. So first, we need to make sure that we have the matching primary or unique constraint in the parent table. And that's easy, we can do it. Then we create this check constraint, which I described from the previous slide, just saying that that's a foreign key. OK, very good. Now we need to check whether there is a validation function. And then I will talk about what is the validation function. If not, create it, and then create the triggers on insert, update, and actually delete as well. And then the creation of the foreign key constraint will be completed. And now the most interesting question, how the validation function should work. Because that's exactly where we need to figure out how we are comparing set of time regions with a set of time regions and how to make it not run forever. And that is like kind of the core of our new part of our improvement of the bitemporal model and implementation in Postgres. So let's first, in order to, again, to understand a little bit more what is the problem, what is the issue with this. So let's look a little bit more about, let's look at the bitemporal queries and what happens with the time regions when we query and we do updates, etc. So again, we just talked about what can be different types of bitemporal queries. The snapshot queries, then interval queries, and correlated queries. So for each of them, different things happen with the time regions of the result sets. Okay, so what we have here? Let's see. Oh, okay, hold on. So how we define time region? So conceptually, think about this. Each row has the associated time region. And when we are executing bitemporal query, we first execute it as if there are no time regions. So we execute it just on the data. So we retrieve the records which satisfy the non-temporal conditions. And then with all these records, we also retrieve their associated time regions. And then we are trying to figure out whether all these time regions together make sense, so how they are related and what will be the result set. So in order to calculate new time region, we will again use intersection, union, and difference. Like, for example, when we have this query, what was the customer type for the customer C100 when, like in September 2015. So what we need to do, we need to retrieve this customer, and then we need to see this time region, okay? Then that's actually the easy one. Then find, so here, for example, what we have, find matching, oops, what happened? Okay. My laptop? Okay, let's see what happened. Yes. No, my laptop is actually fine. I know what happened. Okay. Oh, okay, it works. Cool. All right. So now when we do join, we need to find matching tuples and intersect their regions. So when we want to find what was the status of customer C300 when customer C100 was platinum, so we need to find the time regions for the customer C100 and then intersect it with time regions for the customer C300 and then see what was the type of this customer on the intersection of these time regions. For updates, it's even more complex. So let's say we have the generic update table set attributes to something where condition is something. So if we have as the time region defined by update, so when we actually execute bitemporal update, we have these two parameters, the asserted interval and effective interval. So that is the time region for update. Okay, but is it C? Okay, then for each of the records which are defined by where class, we have this, for each row which is defined by a where clause, we have these old values which got to be updated, and that is P, and then N is the time region for each already existing rows and values. So if as a result of the update, we return the values which are already present, then we need a kind of to put all these time regions together. And after the update, the database will contain this like two time regions actually. One will be region P minus region S, those will be the old values, and S plus N, those will be the new values. So you can see now that they are very far from being rectangulars. Okay. All right. What's that? Oh, sorry. Okay. What we're doing here? Okay, sorry. Okay, here we go. Okay, so in order to like move forward, what we like need to define that we can if we represent each time region as the set of rectangles, then any of the intersection, union, and difference will be also the set of rectangles, because otherwise we're in very bad shape because the results of these operations are not rectangular. And in order to be able to represent each time region as a set of rectangles, we introduce one more operation, which is called disjoin. That's auxiliary operation. So you might think disjoin is we take one region and separate it in like smaller rectangles, but actually disjoin is operation on two time regions. So what we need to do, we need to create set of rectangles so that each pair of rectangles for different arguments either coincide or do not overlap, or do not overlap, or not overlap. Okay, that's a typo. Okay, and then we can perform all our unions, minus and intersect on these subsets, and then life will be much better. Okay, so let's look at the examples, because now it's like, okay, what we're talking about, we were in the realm of times, and now we're in the realm of the rectangles. So that's, and why we need this, first of all, why we need this. So back to foreign keys, what we started, we wanted to figure out how we make sure our validation function works. So now, you think if we can disjoin rectangle from the parent table and disjoin time region from the child table, and then make sure that one set is included in the other set, that means we validated this foreign constraint and everything is correct. So that was whole topic of this exercise. And then later, we did not implement it yet, but later, you know, the stuff which is in gray, those are the future usages of the same operations of the same algorithm. How we are going to do this? Because, yeah, it all looks cool, but if you think about how we approach this, it's very much not obvious. So let's first look at the simpler case, one dimension. Let's say we have only one dimension time, like effective. How we can disjoin two sets of one-dimensional intervals. This is actually much easier. So what you do, you order them in the order of where they begin, and then you like position them like here one after another, and then you cut the smallest pieces between the end of one and beginning of the other, and then you get this little set of like smaller like intervals, which will be disjoint for these two sets of intervals. Now imagine we have two dimensions, and this sounds easy, but actually we can apply the second step of algorithm in the recursive manner. That's how. So those are our two sets. Oh, how we're going to do this. Again, you look at it, you kind of know how they should be separated in the smaller ones, right? You just do not know how to write this algorithm. At least we've been struggling for quite a while on how exactly to write this algorithm. So that's what we're doing. Forget about one dimension. Forget about we have effective. Project everything into asserted dimension, right? And then perform this join on one dimension. So then you will have these stripes. So these stripes is the result of this join on the, like, let's say, here is asserted dimension, if we are consistent with our previous pictures. So we made this join of asserted dimension. Now take each stripe separately and perform this join on each of the stripes. Voila. That's it. This is the result of this join between these two sets of rectangles. And now we can actually validate whether if one of these is the time region for the foreign key, for the parent table, and the other is the time region for the child record. Now we can validate whether one is included into another. So yeah, and this is actually manageable. It's not horrible algorithm. It's very well doable. Okay, thank you. Okay. Oops. Okay. So now the couple of extensions. Oh, okay. What I'm doing again? Sorry. Okay. Okay. So that is like the major improvement for our like support of the foreign key constraints. Now we can do it. So the other great thing which happened for the last year. So I like convinced my company that that's a good way to actually deal with data. So thanks to our technical leadership in Breven Holdings, we were able to implement the bitemporal model in the real-life application. And the moment when we actually started to implement it in real-life application, we found so many issues we never thought about. And yeah, obviously, right? So, and we fixed tons of bugs and introduced tons of things we were missing. So one thing, we introduced bulk operations, because you know what? Okay, we are in the world of relational databases. Our power is with bulk operations. And if you think about the operations we described, all of them were like, unitary operations on one record. So first thing we needed to create bulk insert, because we want to insert data in temporal table. So we added one more function, which is insert select. So the second parameter is not the list of values we insert, but whatever sequel we can use to insert data. Or as well, we can insert like the series of the table of like constant values. Okay. Then same with update, correction, as select. So these ones are in process, but again, the same thing. We now allow, like we are in process of actually creating them. So we are allowing any arbitrary sequel to be used in the where clause and in the set clause. So again, that basically gives us more power. Again, we're updating for the same time region in all this bulk inserts and updates and selects. Consistent transaction behavior. That's other thing we never thought about before we started to face real life. Do you know that financial applications do not like transactional data? Technically, that's who should like it, because we want our accounts to be consistent. But actually, financial applications are oblivious to any of this data, any transactions. So first thing we found, okay, in transaction is atomic. So you are not supposed to see what's happening with the data inside. And what is happening when you are not losing any data? So when you want to update inside transaction, do you want to record this or you do not want to record it? An interesting thing is your first intention, we want to record everything, but actually no, we do not want to record, because then we are exposing the internals of transactions, which is not to be supposed to be, should not be exposed to the outer world. Okay, so we worked with this, and we came up with like the solution. So here is the incorrect behavior. So how we found it? We had update immediately after insert, or in this case, I have correction immediately after update. So remember this slide from the beginning. So if you want to update, not update, to correct immediately after update. And for transaction, the now time is the same. So within transaction, the time is the same. So what you end up with? You end up here with the interval, which has the same begin and start, and it's closed from one side and open another, which is what? It's null interval. So how I found it? I found lots of null intervals in the database. Oh, okay, something is wrong here. So that's how it looks like. So basically, you reduce in this situation the time region free to nothing. And that's not right. So how we are doing it now? Now we corrected this behavior so that you can, so when we are updating or correcting, we check what was the last interval. And if we find that the last interval began at the same time as our current now time, then we do not add new time region, but we override. So that's the only situation under which we actually overwriting the data. But then we preserve transaction consistency. And also, yeah, we allowed, because it's first, oh, no, we want to know what we did. OK, so if you want to be transactionally inconsistent, you can. Because now, again, I'm giving them the like right to pass explicitly the time when this value is going to be asserted. And if you do not want to use transactional time, if you do not want to use now, you can use clock time, and then you will be transactionally inconsistent and you record everything. So now, again, the correct behavior looks like this. So now if we find that we are trying to correct the record which was just inserted with the same effective, with the same asserted start, then we do not insert this record, but instead we correct this record. Okay? So in this situation, there would be no side of somebody being gold, he'll be platinum right away. The other thing is we created high-level functions because application does not need to know all these details. So we were thinking for a while that we need to have high-level functions because they want just insert, update, delete, and they want us to take care of everything else. So we created this set of high-level functions. And performance, that's, OK, so last thing about here, performance. So most of the time when we introduce this bitemporal model, people are, oh, OK, this should be like, this should take ginormous like space on disk A and B. If you have everything in one table, if you do not separate current values in the separate table, the performance will be horrible. So it's not, I can tell you, because it's not. Again, thank you, GIST Index creators. Is actually very, very decent. So, and the size of the tables, actually, I just measured before this conference. So we have about 6 months now of like coexisting bitemporal, non-bitemporal tables. So most of the time with normal behavior, the size of bitemporal table is like 40% more than of the non-bitemporal table, except those special cases when we did expect high level of updates and deletes. GIST indexes are doing great most of the time. Sometimes we need to create additional indices. They also perform great. So far, we have performance on like tens of milliseconds, basically. But again, we did not get really serious volumes, but so far, it's all quite good. So yeah, what's next? So again, you could see from what we just presented that we have several things to be finished. We are finishing implementation of foreign key constraint in its fullest. we are like finalizing all these changes to update and correction, and also we like want to do more research on performance and which indexes should be used, which indexes work, which does not, and what can be done with this. And once again, like we are very thankful for Bremen Holding technical leadership team who like basically gave us this ground to experiment and learn about bitemporal data way more than we would and we did before we started this. So, and that's it. And thank you for your attention and questions. Yes.
Actually, I didn't. So I didn't come to the last year. So but what kind of a problem you try to solve, which cannot be solved different? The common.
Okay. So that was like.
Repeat the question for record. Just repeat the question.
Oh, okay. Yeah. The question was so what problems we are going to solve, and actually I want to get it to the very start because that was basically, yeah. That's already. So most common problem is that people want to see, like if you look at the slide, so those are our most common problems. This is what we want to resolve. Most common because we work in finances, we see these situations when people want to see data how it looked before. And we cannot do it otherwise. So like the snapshot of the data from the past. That's like most common use case. Like if you ever work with finances, it's like very typical you want to run this report for the end of Q3 of last year. Like, very typical.
Yeah, but data warehouse have this changing what called slow changing dimension. All this concept doesn't work for this kind of thing.
So what's the difference? So what's the difference?
It's also the same thing as like multiple records for different times.
It's Oracle's attempt to implement.
No, yeah. So that's the same. Yeah. So the same thing. Yeah. That's the same thing, just a different implementation.
And there's some minor differences too, but they're not strictly relevant.
Oh, yeah. I just wonder what actually I don't understand. Why do we need a foreign key on these things? Like so I try to understand why do you need a foreign key on this?
No, we need foreign key because for the same reason that we need foreign keys in general. Right. You need foreign keys. Like it's no difference. Like you need foreign keys on normal table, you need foreign keys on bitemporal tables.
We want referential integrity to exist, not only between non-temporal tables, but also bitemporal tables to have enforced referential integrity. And that's really the issue.
Any more questions? Yes.
It's not. I was wondering why. So every row stores 4 time points because each.
2 time ranges. No.
Right. To define a range, you need 2 time points.
Yes, but that's one type in Postgres. No, actually, no. That's one of these beauties of Postgres. And again, we utilize the existence of time ranges as types. That's great. And we utilize GIS. GIS does like half of work for us. So basically, you can write this one constraint, GIS with exclusion, and you are taking care of consistency on the two time dimensions.
But then you have to manually ensure that they don't overlap, right?
No, we don't. That's the point. We do not need. We write one constraint, and that's it. No, we never need to manually compare anything.
So I was thinking like you could normalize. You just store 1 time point and then the range.
No. It's a range is one like element, one data element. Ranges are types, and exclusion condition with GIS on time ranges takes care of everything. No, it's
I heard of Postgres' geometric functions. Were those ever useful?
Actually not. We were entertaining this idea like about a year and a half ago, and no, it's actually like better this way. Yeah. Yes, but yeah, we had this temptation to go this way.
Is there a reason why I've never used them? So.
No, geometrical functions. No, we thought about this and did not.
Yeah, we just didn't figure they might be able to, but we weren't smart enough to figure it out.
All right. Was another question? Nope. Question? Nope. Any questions? Nope. All right. Thank you.